Om Swastyastu, Assalamualaikum Warahmatullahi Wabarakatuh, Syallom, Namo Budaya, and good to see you all, guys. And in the Metallurgy, my presentation is about chapter Steel Product and Properties. And I'm Imadi Yudis Chrisantya. I have my ID is 23055310683, and our lecturer is Professor Dr. Tjokorda Gde Tirta Nindhia MT M Eng. And a Metallurgy have a code TM 2301, and I'm from Mechanical Engineering Technical Faculty, Udayana University. And in this my presentation, I take main reference from the book of Metallurgy for Non-Metallurgists, the second edition, edited by Arthur C. Reardon. And now we go to the steel product and properties. The steel product and properties, they have 5 sub-chapter. There is classification of the steel, carbon steel, alloy steel, alloying element in steel, and strength and toughness. Okay, now we go to the first is the classification of steel. The classification of steel from one of the most complex group of alloys in a common use, and there are many ways to classify steel. Classification of steel based on chemical composition is a widely used method. There are 3 very broad-based categories of steel based on composition: is a plain carbon steel, low alloy steel, and high alloy steel, which includes stainless steel. And like we can see in here, there are 2 classification of the ferros. Is like classification by commercial name of application and classification by structure. In the classification in here, they have 3. They have one that is steel, and this steel is 3. The first is plain carbon steel. Low alloy steel is like most 8% alloying elements. High alloy steel or more than 8% alloying elements. And however, it is important to point out that steel are classified in many other ways too. For example, classification may be based on the first is the steel making method, such as open heart basic oxygen process or electric furnace method. The deoxidation practice during steel making, such as kiln, semi-kiln, capped, or remade steel. The solidification method, such ingot casting, continuous casting, or component, like shape casting. The mill product forms, such as bar, plate, sheet, strip, tubbing, or structural shape. The finishing methods, such as hot rolling or cold rolling. The microstructure, such as very thick, fairly thick, and martensitic. The required strength level as specified in standard. The heat treatment, such as annealing, quenching and tempering, and thermomechanical processing. Quality descriptions, such as forging quality and commercial quality. And the steelmaking can be broadly classified into 2 steps: primary steelmaking in a converter or furnace, and secondary steelmaking in a ladle. The 2 most important steelmaking processes are the electric arc furnace, we can see EAF process, the basic oxygen furnace, BOF process, or LD is like Linz-Donowitz process. The EAF process accounts for the 35 to 40% of the world steel production, and BOF produce is in the 55 to 60% of steel. The oxidation practice, oxygen is generally considered an undesirable element in the steel because it combines with other elements. It's like manganese, silicon, aluminum, and titanium to form oxide inclusion that can degrade toughness and fatigue resistance. The solidification method, after steel is melted and refined, it is then solidified into useful forms by various casting methods. On the tonnage basis, most steel is now solidified in continuous casting operation, but casting of the steel still involves the original method of solidifying into ingots. The product forms, various steelmaking product forms called mill product are produced in a steel mills either by continuous casting methods or by the breakdown of ingot into various forms by rolling, drawing, or extrusion operation. The various type of mill steel product include like the first is sheet and a coil of low carbon steel for application ranging from cars to appliances, wire used in such product as bed spring, wire rope, nails, and wire fabric, structure shape used in a building and a bridge, bars for the forging and machined parts such as gear and bearing. Finishing method. The surface of the steel product is influenced by its finishing method. In a rolled milled product, finishing is by either hot rolling or cold rolling. Microstructure. Steel can be classified according to the microstructure at room temperature. Heat treatment are used to produce microstructure that can consist of either perlite, martensite, or bainite, or some combination thereof. Requires strength level, pure casing standard of steel and many other materials often specify a minimum required level of strength, and some categories of steel are defined by their mechanical properties. Another category of the steel based on strength is a group called ultra-high strength steel. These are commercial structure steel capable of minimum yield strength of 1380 MPa is more like 200 KSI, and they have two types of ultra-high strength steel are medium carbon low alloy steel, medium alloy air hardening steel, and the less high alloy hardenable steel. The heat treatment. One of the primary advantages of the steel is their ability to attain high strength through heat treatment while still retaining some degree of ductility. Quality descriptors. Steel are described by a host of quality descriptors depending on the product and type of application. And next, we go to the carbon steel. All the steel are iron carbon alloy with carbon content from 0.02% to less than 2%. The so-called plain carbon steel contains small amount of manganese and silicon carbon steel. As we can see in here, there are two types. The first is manganese carbon, and here is free masoning. And in the SAA, they have most variety of the code, as we can see in here. Carbon steel can be classified further on the basis of carbon content. Steel containing less than 0.30% is called low carbon steel or milled steel, and steel containing between 0.20 and 0.60% C is called medium carbon steel, and steel containing more than 0.60% C is called high carbon steel. And free masoning grades spark pattern can be used to identify low, medium, and high carbon steel. And we can see in here, this is three types of sparks. This is until 0.15% C. This is between 0.45%, and this is between 1.0%. And carbon level have a pronounced effect and properties, and we can see in here this is the variety of the carbon level. And the carbon has very limited solubility in iron, and hard carbide compound Fa3C, it called cemented, forms when carbon is added to iron. And next we go to the alloy steel. In the alloy steel contain manganese, silicon, or copper in a quantities greater than those for the carbon steel, or they have specified range or minimums for one or more of the other alloying elements, such as nickel, chromium, molybdenum, and so forth. Sometimes alloy steel are further defined as being either low alloy steel or high alloy steel, depending is less than 8%. This is not a hard and fast rule, because some steel with alloying slightly above 8% are sometimes referred to as medium alloy steel. And ultra high strength nickel steel. In the high strength low alloy steel, we can see HSLA steel are designed to provide better mechanical properties and or greater resistance to atmospheric corrosion than conventional carbon steel. They are not considered to be alloy steel in a normal sense because they are designed to meet specific mechanical properties rather than a chemical composition. The type of HSLA steel commonly used include weathering steel designed to exhibit superior atmospheric corrosion resistance, control rolled steel, hot rolled according to a predetermined rolling schedule, designed to develop a highly deformed austenite structure that transforms to a very fine aqueous ferrite structure on cooling. Perlite reduced steel strengthened by very fine grained ferrite and precipitation hardening but with low carbon content, and therefore little or no perlite in the microstructure, and a microalloy steel with a very small additional general under 0.10% each of such element as niobium, vanadium, and or titanium for refinement of grain size and or precipitation hardening. Acicular ferrite steel, very low carbon steel with sufficient hardenability to transform on cooling to a very fine high strength acicular ferrite, low carbon bayonet structure rather than the usually polygonal ferrite structure. Dual piece steel processed to a microstructure of ferrite containing small, uniformly distributed regions of high carbon martensite, resulting in a product with a low yield strength and a high rate of working hardening, thus providing a high strength steel of superior formability. In the low alloy steel constitute a category of ferrous materials that exhibit mechanical properties superior to plain carbon steel, resulting from the additions of such alloying elements as nickels, chromium, and molybdenum. High alloy steel with alloying greater than 90% are typically classified as high alloy steel. And stainless steel are the major types of high alloy steel, but two other types are ultra high strength nickel cobalt steel and maraging steel. Ultra high strength nickel cobalt steel we can call Fa9 and I4CO have a good weldability and high fracture toughness. The high nickel content of 9% provides deep hardenability, and toughness, and the 4% CO prevents retention of the excess austenite in a heated part. And next we go to the alloying element in steel. Steel from one of the most complex group of alloy in a common use. The synergistic effect of alloying elements and heat treatment produce a tremendous variety of the microstructures and properties. And they have a lot of properties. Like the first is carbon is the single most important alloying elements in a steel. Manganese is normally present in all commercial steel. Silicon is one of the principal dioxiders used in steel making. Copper in appreciable amounts can be detrimental to hot working operation and has a moderate tendency to segregate. Chromium is generally added to steel to increase resistance to corrosion and oxidation, to increase hardenability, to improve high temperature strength, or to improve abrasion resistance and high carbon composition. Nickel, when used as an alloy element in a constructional steel, is a ferrite strengthener and have most properties is like molybdenum, vanadium, niobium, aluminum, titanium, boron, tungsten, zirconium, calcium, cerium, lead, bismuth, nitrogen, phosphorus, sulfur, hydrogen, tin, and arsenic antimony. And next we go to the strength and the toughness. The word steel has become synonymous with strength, and the description strong as a steel is commonly in everyday language. Steel is usually associated with strength because in many of its use is necessary that steel in one form or another support a load. High strength carbon and low alloy steel have yield strength greater than 275 MPa, is like more 40 kSa, and can be more or less divided into a four classification. The first is as rolled carbon manganese steel, as rolled high strength low alloy. We can see it's like the before is HSLA steel, which are also known as microalloyed steel. Heat treated we can see normalized or quenches and tempered carbon steel. Last is heat treated low alloy steel. And we go to the first is the toughness. Steel are generally considered stout materials, that is, they can absorb the energy of the impact without breaking. Axle shafts and steering components of an automobile are examples of application requiring toughness, because fractures of this component during service would be life-threatening. Fatigue strength. When a steel component is subject to repeat or cyclic stress, including vibratory stress, the part can fail by fatigue even though the bulk stress level acting on the part may be below the yield strength of the steel. The most effective and economical methods of improving fatigue strength involve designing the part to eliminate stress risers, avoiding sharp surface tears or indentation that may result from punching, stamping, shearing, and even hardness testing, preventing the development of surface discontinuities or decarbonization, loss of carbon from the steel at its surface by reaction with the furnace atmosphere during processing of the heat treatment, improving surface finish, and controlling the details of the fabrication and fastening procedures to minimize stress concentration, control of the protection against corrosion, surface-induced nick, and other gouges is an important part of proper maintenance to assure that the fatigue strength is maintained during active service. The importance of the subtle change to the fatigue resistance in a component can be illustrated by examining the behavior of heat-treated alloy steel crankshaft without surface treatment by shot peening is impact the surface of the heat-treated part with steel shot or pellets under controlled conditions. And this is the result of the test on actually crankshaft as well as on a separated test bars. Is also useful in that it show a comparison between the fatigue limit in actual parts in a crankshaft and in a standard test specimen. Correlations are reasonable between the actual parts and longitudinal test bars, which were machined with the axis of the specimen in the same direction as the longitudinal axis of the steel bar or forging from which it was made. In the elevated temperature strength, carbon steel and low alloy steel with a ferrite perlite or ferrite bayonet microstructure are used extensively at elevated temperatures in fossil fuel-fired power generating plants, aircraft power plants, chemical processing plants, and petroleum processing plants. Many applications, however, are even more familiar. Maximum use temperature limit of carbon and low alloy still depend on the application and design criteria. And we can see in the table 8.7 and 8.8, for example, this maximum use temperature in the two specific applications are with different design criteria. In a carbon steel are often used to approximately in a 370 degrees Celsius is 700 degrees Fahrenheit, and here carbon steel have in a Fahrenheit that have 750, and under continuous loading, but also have allowable stress defined up to 540 degrees Celsius. In Fahrenheit is 1000 degrees Fahrenheit. In section number 8 of the ASME Boiler and Pressure Vessel Code, carbon molybdenum steel with 0.5% more use up to 500 degrees Celsius is in Fahrenheit is 1000 degrees Fahrenheit, while low alloy steel with 0.5 until 1.0% more in combination with 0.5 under 9.5% CR, and sometimes other carbide formats such as vanadium, tungsten, niobium, and titanium are used up to approximately in 600 degrees Celsius. In Fahrenheit is 100 to 1000 degrees Celsius degrees Fahrenheit. The effect of temperature on that strength can be measured by short-time tension testing and by testing for creep deformation over time, as noted in the rate of the creep deformation increase and becomes dominant when temperature approaches on the 0.5 Tm, where the Tm is a melting point expressed in absolute temperature in a K. The melting point of the iron is 1813 K or 1540 degrees Celsius, so creep behavior of steel becomes more noticeable at approximately 700 1025 K or 4050 degrees Celsius. And a short time strength of the some chromium-molybdenum steel is compared with low carbon steel. Rupture strengths from the creep deformation are given when temperature exceeds in the 5040 degrees Celsius in a Fahrenheit is 1000 degrees Fahrenheit. The rupture strength of the carbon manganese steel in a 1000 H is on the order of 150 MPa, is like 20 KSI, which is near their yield strength at the 540 degrees Celsius in Fahrenheit is 1000 degrees. Other alloy extend the range of rupture strength in a higher temperature. And we can see in the here they have 75 Fahrenheit, 1000 Fahrenheit, and the difference of A and B. In here we have alloy steel in the 1.0% Cr to 0.5% MO. Is they have only 50 more than 50, and in here in a 1.0% Cr and until 0.5% MO they are between 50. And we go to the corrosion. The word corrode is divided from the Latin corrodere, which means to piece. Corrosion takes on many forms and can be defined in many ways for the purpose presented here. The metallurgical definition of corrosion is an electrochemical process whereby metal atoms exchange electrons with atoms in the environment. Thank you for watching my presentation. I hope you all can receive what I can say in this presentation, and forgive me when I have some wrong words or anything else, and I will close with Om Santi 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 Om. Assalamualaikum warahmatullahi wabarakatuh. Shalom, and see you guys.